Okay, this is the discussion 1-3 for Chem 1 on electron configuration. So we're going to learn how to do electron configurations and orbital notation. All right, so we did that in class. We're not going to do that right now. So when we talk about the modern atom, when you were in middle school, you probably learned about the Bohr model, and maybe you even had to make a Bohr model. And the idea of the Bohr model is that we have a nucleus with protons and neutrons, and then electrons are moving in fixed orbits, kind of like planets around the sun. Now, this isn't really accurate because we know that electrons don't move in these calm, peaceful little orbits, right? They actually move randomly and very quickly. Okay, so in our modern model, we know that electrons move randomly in the electron cloud, and we can predict their location based on probability. So Schrödinger and Heisenberg were two of the people that contributed to this model, and Schrödinger developed an equation to predict electron location, and Heisenberg developed his uncertainty principle. The basic take-home message of the uncertainty principle is that we can know the speed of an electron or its position, but we can't know both at the same time. I told an amazing joke in class, so if you want to hear it, let me know and I will tell you. All right, so in the early 1900s, scientists noticed that certain elements, when they were put into flame, had a distinctive color. So when they analyzed the light, they found out that an element's chemical behavior is related to the arrangement of its electrons. And so each atom has a sort of distinctive color that's produced when it's put into a flame. Now, when we talk about the arrangement of these elements, we have to talk about sublevels and orbitals. So orbitals are basically just the places where electrons are located. So we have S, P, D, and F sublevels that contain S, P, D, and F orbitals. The S orbitals are spherically shaped. The P orbitals kind of look like a dumbbell, or you can say it looks like a peanut because that starts with P, and D kind of looks like a dragonfly. And you can sort of think of these as like the rooms where electrons live, okay? And 2 electrons can go in each orbital. Now, looking at the periodic table, the periods, or rows on the periodic table, represent the energy levels. So if an element is in period 3, it has 3 occupied energy levels. S, P, D, and F are the sublevels. Okay, so when an electron is added in the S sublevel, it goes into an S orbital. And every time we go through one more box on the periodic table, we add one more electron. Now notice, the S block, those 2 columns, it's 2 columns wide, okay? The P block is 6 columns wide, the D block is 10 columns wide, and the F block is 14 columns wide. So the S sublevel has 1 orbital that can contain 2 electrons. So every orbital can hold 2 electrons. So if there are 3 p orbitals, how many electrons would there be? Also remember, the p block is 6 columns wide. So those 3 p orbitals can hold 6 electrons. For D and F, the 5 d orbitals can hold 10 electrons, and the 7 f orbitals can hold 14 electrons. Now, let's talk about how we write electron configurations. So electron configurations are basically used to tell us where every electron in an atom lives, okay? And the lowest energy arrangement of electrons is called the ground state configuration. Now, every electron configuration we do in this class is going to be a ground state electron configuration. I'm telling you that so if you see it, you're not alarmed. The ground state is just the normal electron configuration. So let's look at hydrogen. Hydrogen has only 1 electron, and its configuration is 1s1. So let's talk about what each of those numbers and letters means. So the coefficient, the large number, tells me what energy level we're talking about. So what period is this electron in? The S tells me the sublevel. So what region on the periodic table did this electron get added in? And then the superscripted number tells me how many electrons. So what this means is that hydrogen has 1 electron in the first energy level, s orbital. So we call it 1s1. All right, so let's try a few together, and I'm going to go to the document camera for this. We're going to do nitrogen and magnesium. Okay, so when I write the configuration for nitrogen, let's focus that. All right, nitrogen's here. And what I'm going to do is I'm going to go through every period on the periodic table until I get to nitrogen. So I start at the very beginning. I'm in period 1, S block. And I have to ask myself, how many electrons do I add in the first energy level S block? So basically, how many squares do I go through? Now remember, helium is located over here because it shares properties with these elements, but it's really in the S block in terms of electrons. So I wrote it here just for the purposes of this discussion. Okay, so in the first energy level S block, I go 1, 2 squares. That means I'm adding 2 electrons in the first energy level S orbital. Okay. Now, I haven't gotten to nitrogen yet, so that means I have to keep going. Right, so now I come down to the second period. So now I'm in period 2. I'm still in the S block, and I go 1, 2 squares in the second energy level S block. So far I have 2 electrons in the first energy level S orbital, 2 electrons in the second energy level S orbital, but I haven't gotten to nitrogen yet, so I have to keep going. So now I keep going across this period. Now I'm still in period 2, but now I'm in the P block. So that means these electrons are going into P orbitals. So now I have to ask myself, how many squares do I go to get to nitrogen? 1, 2, 3. So that means that 3 electrons are going into the second energy level, P orbitals. Okay? Now, when I look at all these superscripted numbers and add them together, 2 plus 2 plus 3 equals 7. I have 7 electrons. Does that make sense for nitrogen? Well, sure, because nitrogen has an atomic number of 7. So in a neutral nitrogen atom, there should be 7 electrons. So that's one way to kind of check and see if I've probably done it right. All right, so let's look at magnesium now. We're going to do the exact same thing. We're going to start at the beginning and go through every row until I get to magnesium. So I start in period 1, and I'm in the S block. And I go 2 squares in 1s. So it's 1s2. So my first 2 electrons are in 1s. You're going to notice we're pretty much always going to start this way. Okay? Now, I'm in period 2. I'm still in the S block. And how many squares do I go? 1, 2. I still haven't gotten to magnesium, so I have to keep going. So now I come over here. I'm still in period 2, but now I'm in the P block. So how many squares do I go? 1, 2, 3, 4, 5, 6. So in 2p, I'm adding 6 electrons. Still haven't gotten to magnesium, have to keep going. So now I'm in period 3. I'm back in the S block. And how many squares do I go to get to magnesium? I go 2. So what this means is that I have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 6 electrons in the 2p orbitals, and 2 electrons in the 3s orbital. And again, when I add these all together, I get 12, and that's how many electrons magnesium has. All right, so which element has the electron configuration 1s2, 2s2, 2p2? So pause for a second, see if you can figure it out, and press play when you're ready. Okay. So 1s2, 2s2, 2p2. So let's go through. 1s, well that's right here, 2. All right? 2s2, and 2p2. All right, so this is 2p. When I go 2 squares, that would be carbon. So the answer is carbon. Okay? I want you to try to do the electron configurations for fluorine and aluminum. So fluorine and aluminum. So go ahead and try those on your own, and then press play when you're ready to go over them. So fluorine and aluminum. Okay, so let's look at fluorine. I start at the beginning, period 1. S block, and I go 2 squares. Still haven't gotten to fluorine, so I have to keep going. Now I'm in period 2, still the S block, and I go 1, 2 squares. I come over here, I'm in period 2, but the P block now, and how many do I have to go to get to fluorine? 1, 2, 3, 4, 5. So I write 2p5. Okay. For aluminum, again, same process. I start at the beginning. I'm in period 1, the s block, and how many squares do I have to go? 1, 2. Now I come down here. I'm in period 2, the s block, 1, 2 squares. I come over here, period 2, p block, and I go 1, 2, 3, 4, 5, 6. I come down here, period 3, s block, 1, 2. And now I come across here. I'm still in period 3, but now the p block, and I have to go 1 square in to get to aluminum. Okay? All right. So let's talk about orbital diagrams. So orbital diagrams are really just a way to show electron configurations visually. We use arrows to represent electrons, and we use boxes or lines to represent orbitals. So every orbital can hold 2 electrons, and we draw one pointing up and one pointing down in a single orbital. We'll talk about why in a minute. Okay, so this is the orbital diagram for sodium. Now, sodium's configuration is 1s2, so there's 2 electrons in the 1s orbital, 1 up, 1 down. 2s2, so 1 up, 1 down. 2p6, so we have 6 electrons in those 3 orbitals, 2 in each, and 3s1. Now, there's some rules that we use to put electrons in orbitals. So the first is called the Aufbau principle, and this just says that electrons fill the lowest energy level first. Just like if you had a 20-story apartment building with no elevator, people would want to live on the ground floor, right? 'Cause it takes a lot of energy to get to the top apartments. It takes a lot of energy to get to the upper energy levels. So that's why all these configurations that we've done so far start with 1s, right? Because electrons fill the lowest energy level first. The Pauli exclusion principle says that orbitals can hold only 2 electrons and they should have opposite spin. So we're going to show the spin with the arrow direction. So that just means in a single orbital, I can have an arrow pointing up and an arrow pointing down. The last rule is Hunds Rule, and sometimes we call this the kids on a bus rule. So when we have more than one of the same orbital, for example, the 2p orbitals, there's 3 of them. When I'm putting electrons in them, I put 1 electron in each orbital before I pair them up. So for example, nitrogen. This would not be correct because it violates Hunds' rule, okay? We paired up, in this incorrect diagram, we've paired up the first 2 electrons, but it should look like this, with 1 electron in each of the 2p orbitals. And this makes sense, right? Electrons are negative, so that means they repel each other. So it makes sense that we would put them alone before we pair them up. Okay, so let's do carbon together as an example, and then I will have you try pause and try fluorine and magnesium. Okay, so carbon, its configuration is 1s2, 2s2, 2p2. So you can either do lines for the orbitals, or you can draw boxes. It doesn't matter. I sometimes like to draw boxes, but they're equally correct. Okay? All right, so 1s2. That means I need to put 2 electrons in this 1s orbital. So I'll draw 1 up and 1 down. 2s2. That means I need 2 electrons in the 2s orbital. 1 up, 1 down. 2p2. Okay, so when I put those 2 electrons in these p orbitals, I have a choice, right? I could put 2 in this first one, 1 up, 1 down, or I could separate them. And according to Hunds' rule, the correct thing to do is to put 1 in each and only pair up if I have to. I have an empty 2p orbital. That's totally fine. All right, so I want you to pause for a sec. Try fluorine and magnesium. And we already did their electron configurations up here, so you can use those to help you. Okay? Should have left a little more space. All right, so press play when you're ready to go over them. Okay, so for fluorine, we have 1s, 2s, and 2p. And again, this is just a visual of this electron configuration. So 1s, 2. So in the first energy level s orbital, I have 2 electrons. 2s2, and 2p5. So that means I need to put 5 electrons in these 2p orbitals. 1, 2, 3. Okay, now I have to pair up. 4, 5. Okay. All right, magnesium, same basic idea. 1s, 2s, 2p, and 3s. All right, so looking at the configuration, 1s, 2. 1 up, 1 down. 2s, 2. So I need 2 electrons in here. 1 up, 1 down. 2p, 6. So 1, 2, 3. I do have to pair up. 4, 5, 6. And 3s2. 1 up, 1 down. So if you can do the electron configurations, this is not so difficult. So it's important to master the electron configurations first and then come back and get good at the orbital notation. Okay? So the last couple things I want to talk about are shorthand configuration. So some of these electron configurations get kind of obnoxiously long, right? So we have a shorter way of writing them. So what we can do is we can use the noble gas that came right before that element to represent the configuration up to that point. So noble gases are the elements in group 18, and since they're at the end of the row, they have full outer energy levels. So noble gases are really stable, and so that's what we're going to do. You can't put anything else in brackets, only noble gases, so only group 18. So for potassium, this is the configuration. That's kind of annoyingly long to write. So instead of all that, we say, okay, I'm going to look at the periodic table, and I'm going to say, which noble gas came right before potassium? So here's potassium. Looking back, these are my noble gases. Well, right before potassium, I went to argon. So what I'll do is I'll write argon in brackets. Okay. And then I just have to write whatever comes after that. So what period am I in? 4. What block? S. And how many squares to potassium? 1. So it's quite a lot faster. All right, so let's do one more example together. Let's do silicon, and then I'll have you try magnesium and chlorine. All right, so silicon would look like this. Okay, here's silicon. So what noble gas did I get to right before silicon? Looking backwards, it was neon. Okay, so after neon, I have period 3, the S block, 2 electrons, and period 3, the P block, 2 electrons. Okay, so I want you to try magnesium and chlorine. Pause and then press play when you're ready to go over it. Okay, so for magnesium, it's right here. The noble gas that came before it was neon as well. Now we're in period 3, the S block, and I have to go 2 squares to get to magnesium. So this is a lot faster. For chlorine, again, the noble gas that came before is neon. So then I come down here. I'm in period 3, the S block, and I go 2 squares. Now I come over here. I'm in period 3, but the P block, and I go 1, 2, 3, 4, 5 squares. All right, so the noble gases are really important. They're the most stable since they have full outer energy levels. And so one of the things that we're going to talk about as we move through the class is that when atoms gain or lose electrons, they gain or lose so that they have the same number of electrons as the noble gases. So for example, oxygen is going to gain 2 electrons to be like neon. Sodium will lose 1 electron to be like neon. So we'll focus on this a little more in the coming units. Now, valence electrons are really important because they're electrons in the outermost energy level of an atom. And they determine all of the properties of an element. They determine its reactivity. So we can find these from electron configurations. And elements with the same number of valence electrons will have similar reactivity. So in red is the outer energy level. So the outer energy level for lithium is 2. And in the second energy level, s orbital, it has 1 valence electron. For beryllium, the outer energy level is also 2. but now there's 2 electrons in that energy level. For boron, the outer energy level is 2, and in that second energy level, we have an s orbital and a p orbital that are occupied, with 3 total electrons. Sodium's outer energy level is 3, and it has 1 valence electron. Now, if you wanted to write the electron configuration to figure out valence electrons every time, you could, but there's a much faster way. The easiest way is to look at the group number on the periodic table. So, everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Group 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18 has 8. So, how many valence electrons does arsenic have? Well, it's in group 15, so it has 5. How many valence electrons does rubidium have? Well, it's in group 1, so it has 1. How many does xenon have? It's in group 18, so it has 8. Okay, so this is a lot to process. The main thing to do is to practice as much as you possibly can, and come see me if you have questions or need help.